So I'm your workshop host for today, Matt White. I am the Executive Director at the PyTorch Foundation and the GM of AI at the Linux Foundation. As mentioned, we've got a pretty great agenda here. Speakers from Red Hat, Anthropic, Anyscale, Unsloth, and Google. And I'm going to just say a few words on open source AI and open standards, and then I think the best thing to do is get right into the talks. So one thing I want to just address up front here is this confusion around openness. We have a lot of folks saying, yes, this is open source, our project open source, our model's open model, whatever. But I want to introduce these concepts of completeness and openness because it helps kind of clear up these muddy waters. Completeness, this is sort of a concept that we borrowed from open science where we talk about, okay, very thorough research papers, you release all artifacts with a model, let's say, its weights, intermediate steps, so forth. And then we have this concept of openness, which really boils down to it's open or it's not open. And that follows the principles of open source. So being able to study, use, modify, so forth, for any purpose. And the challenge that we see today is there's a lot of folks saying, hey, this is an open model. It's not really an open source model because it has a bunch of restrictions in place. And so what we want to do is make sure that as we build an agentic future, that future embodies this principle of openness, right? That we're not holding back, that we're not hiding things behind the scenes, right? That we're releasing, particularly in open science, which we're seeing sort of threatened right now, which a lot of labs are holding back and not releasing a full research papers. They're releasing technical reports, and we just want to make sure that we stay, faithful to ourselves and our principles, and especially in research, that we release all details and all components, and that's how we can build a better agentic future that's open. So the benefits are, very obvious around, openness, right? Being able to build the sort of modular components that are needed to be able to then work off of and build off of and innovate, and so we can continue to build and build these agentic components, right? And so prototyping and particularly domain-specific adaptation, it takes a lot of time to develop for a particular domain, and when we release those domain-specific adaptations or domain-specific deployments in open source, it makes it a lot easier for others to adopt those and employ those in their enterprises or their organizations. We can't forget about safety and trust, especially in an agentic world. We do need controllability. We need observability. If anyone's spent time trying to debug what's happening with their agent, sometimes it's sort of like a fruitless endeavor. And then safety. In the industry, we've kind of forgot about safety again, kind of also we forgot about security. And so we need to remember that these are two very important guiding stars for us. And then interoperability is going to be a huge thing, right? So we have protocols that are becoming sort of standard now, A to A, MCP, and so forth. But if we don't build standards collaboratively and they're not open standards, then we will have protocol wars and a lot of interoperability issues that will sort of become a problem at some point. So, and there's just one thing I want to mention on open standards. So there's this new paradigm in open standards development, which is developing open standards like you develop open source. And so traditionally, folks would start a small steering group, develop a protocol, and then send that to W3C or ITF for ratification. Now we're seeing standards being developed in the open, which I think is a much nicer paradigm. It creates a lot of transparency. You can engage the community and help work towards collaborative spec development. And so this is how MCP is being developed, right? And so, we talk about, if you have, you have something you want to implement, you create an issue for it, and then engage the community and let the maintainers review it and provide feedback. So I'm good with that. We have 5 speakers in an hour, and so I want to make sure that everybody has time to speak. And I think the best demonstration of open source and open standards is to allow these project maintainers to speak about their projects. So thank you very much, and we'll move to our first speaker. So our first speaker is Michael Goen, who's a principal engineer at Red Hat, and he'll be speaking on accelerating agent scalable and efficient inference with VLLM.
Hi, everyone. My name is Michael Goen. I'm a principal engineer at Red Hat. I was previously an engineering lead at Neural Magic. We were acquired by Red Hat at the end of last year. We've been working on VLM for over a year and a half now, particularly on a lot of the performance engineering and inference optimization parts. So yeah, I wanted to give this talk on what is VLM, why is it important for LLM inference, what does it implement, and why is that important for agents? So first, it's important to state what is VLM's goal. It's a pretty simple and easy one: build the fastest and easiest to use open source LLM inference and serving engine. But first, before we think about that goal, we need to talk about what problem is VLM setting out to solve. So it's really, really important to say it's solving batch size greater than 1, and it's targeting data center hardware, the really expensive H200s, B200s of the world. This is unfortunately not the same workload as trying to run a 2-bit model on your laptop serving just yourself. Still use Olama and Llama.cvp for that. We love them. But when you're talking about this problem in this scale, we need to think about how do you efficiently schedule requests on each forward pass that you're going through the model as these requests are constantly coming in and out of scheduling. Like think about serving a web server or a database at scale. We need to really think about scheduling efficiently. And then how do we manage the compute and memory requirements that come with LLM inference, like the very large KV caches we need to deal with long context workloads that agents love. So taking another step back and reminding what LLM inference is and why is this a hard problem. So if you forget about all the parameters and operations, an LLM is a function to predict the next token in a sequence. And to generate text or generate multimodal output, we need to chain together multiple forward passes through the model to generate each token in succession. So you see on the image on the right, sort of the yellow tokens are our input or our prefill that we process on the first step. And then the blue tokens that we're building up on each time step as we go down are our output or our decode tokens. And so a single request can take hundreds, thousands, tens of thousands of steps or forward passes through the model in order to generate all the tokens you need in your response. And so this obviously isn't efficient if you need thousands of requests for a single request. So how do we batch these requests together? So when you talk about batching, really kind of before LLMs, static batching was really popular. However, because of these autoregressive workloads can go on for very different amounts of lengths. You have some requests that finish in 10 tokens, some that finish in 100,000 tokens. If you batch all the requests together and keep that static, you end up with a lot of empty space and wasted work as you're going through these time steps here where we've already hit our end tokens and we're just haven't scheduled anything else. So obviously one of the most important things that were implemented was continuous batching, so that when a request finishes and we have our static batch, we can just insert in new requests that can prefill and run and start fitting inside the existing static batch. Second challenge is KV cache. So KV cache is the idea of if you keep around these two key vectors for each token, keys and value vectors, you can skip a lot of computation for all the previous tokens that you've seen in your context. And now the bulk of your computation is just on the new tokens that you need to process and are generating. This is obviously a great optimization, but it takes some memory cost. And maybe you only need 1 megabyte for each token that you have in KV cache. But when we're talking about 100K context, 1 million context, that turns into gigabytes. And then you talk about wanting to batch requests together, that turns into hundreds of gigabytes. And in large production scenarios, the KV cache ends up taking more space than the model parameters themselves. And so what VLM introduced in order to make this management easy is paged attention, which is an attention algorithm that is based on virtual memory, kind of taking the idea from operating systems, that's where the V in VLM comes from, and introducing this block table, which gives us a layer of indirection so that the request thinks it has tokens in contiguous memory, but in actuality, these can be stored completely discontinuously in memory. As you can see here, we have 2 requests that are running. They have their own block tables. They think they have their own logical KV blocks, But in physical memory, these can be interspersed and reused even across requests. So that was the start and the genesis of VLM. You can see the paper on the left. And it's been a very rapid 2.5-year journey now of 50,000 GitHub stars, over 1,000 contributors, a ton of usage by the frontier model labs, by industry, by researchers, and it's really served as a great catalyst. And so I'm going to talk about why it has become that important catalyst. Of course, page attention fits in the optimizations there, but there's many other types of inference optimizations that have arisen since then, like chunk prefill, distributed inference, multi-layer batching. VLM has kept up in implementing a lot of these. But then, of course, there's the 100+ model architectures that VLM supports within this software infrastructure. And then, of course, the different hardware providers have taken the opportunity in order to use this software interface and build their hardware backends in order to harness and fit in this abstract software layer. So now I'm going to dive into a few optimizations with VLM and what are we doing these days? So a really key one is automatic prefix caching. This is actually a really elegant optimization that comes from page detention naturally. If you do like multi-turn conversations or RAG where you're reusing shared context from requests, page detention just gives you this automatically because you already have the KV blocks in your memory, and for the next request, you just fill in its block table with the blocks that are already there in memory. So you can skip a lot of time in prefill, and this really helps improve both time to first token and your token throughput as you get higher and higher cache hit rates. This also works for multimodal data. It's a really powerful idea. Another key idea is quantization. You're probably familiar with this from other projects that mostly focus on weight-only quantization. We also focus a lot on activation quantization, so quantizing both the weights and the activations, allowing us to use those lower precision tensor cores and get more compute, more throughput out of the server that we're serving. And you can see we're sort of comparing unquantized versus 4-bit weight-only quantization versus 8-bit activation quantization. And as we scale the queries per second or users per second, we're able to serve a much lower latency and serve more users within our latency requirement with these types of quantization. And of course, KV cache quantization. We want to shrink the KV cache so we can do more batching and have efficient inference. Next, there's also speculative decoding. There's many methods to do this, but generally it's the idea of using some cheap way to generate many different candidate tokens and then passing those candidate tokens in parallel through your target model and then reading the output log probs to understand would the model have predicted these tokens anyway, and if they did, great, you predicted 3 tokens at once instead of 1 token at once. This really helps in the low batch size regime, pushing latency even lower and increasing your tokens per user per second, which is really critical for coding agents, for anything that you want to get a response faster, get tool calls faster, all those great things. And of course, with VLM, you're not choosing one of these optimizations. You're able to compound and stack these optimizations together as a system, offering compounding benefits. Now all those optimizations are talking about single node inference. VLM can of course go distributed, distributing your model across devices on a node and even onto multi-node cluster scale inference. So I don't have a lot of time, so I won't go over different types of parallelism, but we have tensor, pipeline, expert, data parallelism. These are all useful in different scenarios. And again, VLM can mix these types of parallelism together where you would like to do so in very different workloads. For instance, it's very different. You want to use tensor and pipeline parallelism when you're hosting a dense model like Llama 405B, but you would much rather use data parallel and expert parallelism when you're hosting a very fine-grained, sparse mixture of expert model like DeepSeek v3. And finally, there's the idea of disaggregated serving, where we can actually separate the prefill operation from the decode operation. This is a really important operation for like production usage, because this now means new requests coming in are not going to affect our latency or our sort of user metrics as we're decoding. Prefill is very, very compute-bound type of workload. Decode is much more memory-bound because we have less tokens we're processing. We're reading KV cache where we don't have that great of a batch size. So that's all I wanted to cover really quickly. Only had 10 minutes, so sad. But hopefully you learned some and happy to talk afterwards. Thanks to the over 1,300 contributors we now have in the project. It's a pretty insane metric. Yeah, check it out on GitHub. There's several other projects under the VLM project, LLM compressor, AI bricks, production stack, many other things. And please get involved. Check out the issues, check out the PRs. Let us know on GitHub if there's some feature you really want. Join the Slack and join office hours. We host these bi-weekly office hours that let you know what's coming, what's new in each release, and also have special topics with people from the community presenting on what they do in VLM. So that's all. Thank you.
All right, thanks, Michael. Our next speaker is Jason Kim from Anthropic, speaking on MCP as a foundational protocol for agents.
My name is Jason Kim. I'm an engineer from Anthropic, and I'm here to speak about MCP. Thanks to Matt and RDI for hosting in this very crowded but nicely stained glass room. Anthropic has many UC Berkeley alumni or people who are associated, and so I won the battle royale internally to get to speak this time, but surely I won't be so lucky next time. In today's talk, we're here to talk about MCP as a foundational protocol for agents, and we hope this will tie into a lot of the other sessions that you're hearing throughout the day as well. Claude made most of these slides for me with MCP servers, so hopefully there are no surprises, but if there are, surely we'll discover them together. Before I really get started, I think it's kind of important in these talks to try and say the most important thing at the start and at the end, so that if you get a really good push notification in the middle, you still sort of got 90% of what's going on. I think the most important thing is sort of a request from Anthropic and from the MCP community. This is a newer open source standard, and we'd really like your participation. Read the docs, implement it yourself, PR against the spec, against the reference implementations, join the Discord, become a maintainer. These are all things that are helpful, we hope, to everyone, and so we'd really sort of request your feedback and whatever it takes to get involved. All right, so let's talk about MCP. Why are we doing this necessarily? The premise is that we believe, and I think most people agree, models are only as good as the context provided to them. Put another way, Anthropic is an AI safety research lab. The first public product we made was a powerful family of large language models called Claude. We have a number of tools that use Claude as well. But something we're finding lately is that if we have to make a trade-off on incremental benefit, it seems better to spend time giving models context rather than making the base model just a little bit smarter. Actually, I think this concept sort of applies to humans as well. Think about if you were going to hire me to work on your company or your project. It's probably better for you to just hire me now and give me a week of onboarding than to say, like, Jason, go study for a week and make your IQ like 2 points higher. This specific context is really important, and so we want to design MCP to make it easier to accomplish this task. This task is in service of this overarching agentic implementation that you've heard a lot about. It was mentioned in the keynote that would just happen before this, before we all sort of like ran up the stairs and came here. As part of giving context to a large language model, what do we mean by this? We mean some of these purple boxes that are at the bottom. We want to give the models up-to-date data that it can retrieve in service of a request. We want to give it tools so that it can call and affect the environment around us. And we want to give it memory so that it doesn't make the same mistakes over and over again. If you've watched early versions of Claude Plays Pokemon, you know why memory is so important. We spend a lot of time sort of getting trapped in these trivial cases. And so how does MCP solve this? We've designed MCP to be an open protocol that standardizes the interface between AI-based applications and agents and the context that we're trying to give them individually. Again, context meaning tools, data sources, interfaces, possibly even other models or other agents themselves. We believe using MCP and adopting it more thoroughly can help us speed up this integration process. We're always working on security, which has been quite core to Anthropic's mission and has roots both in the open source and the enterprise community. And frankly, one of the most exciting benefits is to MCP is to allow us to take advantage of the growing community around us. Every room today is so full, and the registration line was so long, and there's so many people online, and it would be a shame if we couldn't take advantage of the things that we're building. if it's shareable, if we can implement them in each other's projects and pass those back and forth. The sharing thing is a little tricky because before MCP, we had a lot of parallel development. And I think this would happen within project teams, within companies, within customer groups. Everyone would go ahead and build their own implementation. So you'd see something in a session and you'd say, this sounds really cool. I've gone and built a project with Claude. I wrote some prompts. I did some API plumbing. I handled authentication. Maybe I wired up a little bit of a test set. And then if anyone wants to do this again, they sort of repeat this process in a vacuum, right? It's like we're never talking to each other except to share weird examples of things that went out of bounds. The advantage to MCP, we hope, is to allow for standardized AI development. There's two parties, so to speak, in the MCP ecosystem: MCP clients, which make requests and connect to these external sources of context, and MCP servers, which are the ones that nominate and provide this context themselves. We've already been doing a lot of this context providing manually. If you think about times you've hooked up a database or an API or a local file system tool to Claude, these are all examples of context that we provide on the MCP server side. And the hope is that we can make these things usable and reusable rather than having to rebuild this thing every time something changes in the space, every time a new model is made available. We know from past track record these changes happen quite often, and so having this approach for standardization, we hope will make it easier for us to adopt. What can you do with MCP? I think there's a lot of examples, and I'm sort of interested to see yours. But one example we'll look at here briefly is providing this external context for things that models might know. We can assign Claude tickets in a software engineering context, which you might have seen if you've used Claude Code. And in this case, we can allow Claude to do things like look at our intercom tickets, look at underlying linear issues, reach out to the code base, author commits. These are all actions that Claude doesn't have built into it necessarily, but it's interacting with the world around it. And this type of MCP server approach is the way that we hope we can provide this sort of external context, taking advantage of what other people have built and specialized in. Linear or Intercom or GitHub or whoever, they might have already built an MCP server, and we want to borrow from that so that we can focus on what we want to build ourselves with an LLM. When I was building this, Claude was worried that we might not have internet in this room, so it gave me a screenshot of the same thing as well. We were prepared. So we won't do a full deep dive because of time. I think as I meant what I said up front is we do really want you to go read the spec, read the reference implementations, humbly give feedback to the community on ways this can be clarified. But I do want this to sort of get you thinking perhaps of how this might mesh with the other speakers and the other sessions you might hear today. We talked about this difference between MCP clients, which sort of invoke these context actions, and MCP servers, which expose these actions to us. These are all sort of areas that you might sort of have gone through in your own approach, and so these are options that you have in terms of borrowing from MCP-based components today. I think we've sort of talked about this before. There's room for people on both sides. Building a client allows you to connect to this network of approaches that other people might have already made available. And building a server allows you to sort of expose a best practice or an interface. If agents are going to use your tool or service or backend or front end increasingly often, you might want to give them guidance on how to use it the same way you would give humans guidance as well. So we're authoring approaches for agents as well as for humans. We're always doing new things on MCP. This is the spec revision from last month. We're probably about due for a new one, so stay tuned for more details. You can read about this as well. And in fact, the place to read about this all that I keep referencing is here just for sort of specific reference. I think I'll sort of close this by going back to what I said at the start. Remember the most important thing. We really do want your engagement as much as possible in terms of joining the community, interacting with the reference implementation, giving feedback on the spec, joining the Discord. MCP is much bigger than Anthropic at this point in time. The success of it is going to sort of involve everyone in the community, but if there are things that Anthropic or myself can do somehow to make it easier or better for you to interact with the MCP spec, please do let me know or let us know. I think this is sort of the main goal we have in mind, and it'll be exciting to see what we can build and what the spec will look like in 2 or 3 months from now. So looking forward to it. Thank you.
Thank you, Jason. Our next speaker is Sumanth Hedge from Anyscale, and he'll be speaking about Ray Scalable Agent Infrastructure. Thanks.
Everyone, I'm Sumant. I'm a software engineer at Anyscale, and I'm going to be talking about Ray as scalable agent infrastructure. More specifically, I'm going to talk about training as well as deploying agents with Ray. So as you're all aware, we've seen some great progress in post-training this year, specifically around using RL for training models for reasoning as well as agentic tasks. Two great examples we've all seen are DeepSeek R1, which achieved great progress in reasoning with RL, and also Deep Research from OpenAI, which was an agent for multi-step research, again trained with RL. We've also seen some great agent applications this year with Claude Code, Manus. More recently, we had OpenAI bring out their agent. So I'm going to be talking about both of these components, how you can train as well as deploy agents. Before we get started, so Ray is an open source project that I work on. It's built around scaling compute-intensive AI workloads. We have a great community with more than 50,000 developers and more than 1,000 open source contributors from leading AI companies who are working with and contributing to Ray, such as Canva, Apple, Meta, OpenAI, etc. Okay, so I'll largely focus on training and specifically training agents and post-training with Ray, but I'll also get to deploying agents at the end. Okay, so if you look at open source libraries right now for post-training who have some focus on scalability, they're all built on top of Ray. So post-training right now runs on Ray. And if you look at libraries like OpenRLHF, Whirl from ByteDance, NemoRL from NVIDIA, and SkyRL, which is a newer project that I work on, all of these are built on top of Ray. Before we get into how we're using Ray for post-training, let's try to understand why large-scale RL is hard. Broadly speaking, you have two components, the trainer and the generator. And if you go one level further, you actually have three components in RL, the trainer, the inference engine, and the environment. And you typically have like specialized frameworks that you're using for each of these. So you'll use FSDP maybe for training. You'll probably use something like VLLM for inference. And you'll be scaling these in different ways. You'll also have to now manage sending data around these different components. So for example, rollouts from replicas of your inference engine to your environment, and then getting observations back. And then once you've actually collected like maybe a multi-turn trajectory, you'll send these to your trainer, and you again have to deal with like maybe multiple models in your trainer for your final optimization step. So all in all, you have a lot of these moving parts, and we'll go into how Ray can help manage this complexity. Before I go into the details, I actually want to take a step back and give some background on some of the core APIs of Ray. This is going to be a bit different, but these basic building blocks that I'll show here are how we're going to actually build complex applications like scaling post-training. So what I got here is actually two simple functions around reading an array and then adding them up with NumPy. And the way you'd convert functions to Ray tasks would be to use this Ray remote decorator. And then you'll also change your function call to use this remote keyword. And what could happen is, for example, you could have the reads run in two separate nodes, and maybe the computation run in a different node. And the return values from these function calls are object references or futures. So you would resolve these with a ray.get call. Similarly, you can also look at translating like regular Python classes to Ray actors, and you'd use the Ray remote decorator again. Lastly, you can also add in resource constraints for your tasks and actors. So for example, your inference actor can request 1 GPU, and Ray will appropriately schedule this on a GPU-enabled node. Okay, so again, these are like low-level distributed computing APIs. We're gonna now like tie this back into what we're interested in, which is RL. The main place where Ray fits in here in terms of training is in orchestration. So Ray will handle setting up these different processes, managing, scheduling these on the resources that you want, also around handling data communication between these different components, and also things around auto-scaling and fault tolerance. So what I've shown here is how you might have set up your training inference engine in your environment components. You can probably have reactors for each rank of FSDP that you're managing for different models. You can also have a reactor for managing replicas of VLLM in your inference engine. And you can also have reactors for scaling out observations in your, for getting observations from your environment. Okay, I will also actually look at some high-level training code just to like kind of show how like Ray has simplified managing this data flow in RL. So again, we're dealing with like regular Python classes here, and we'll convert them to reactors with the Ray remote decorator. And then you can instantiate these and with like maybe some specific resources, and also scale, like put down your like desired world size in some sense. Before we go into how maybe training might look like, I've defined this tiny like helper class here called an actor group just to make writing down the training loop easier. This is essentially just instantiating a group of actors, adding some specific options, maybe around scheduling it on a particular set of GPUs in your cluster. And then there's the special forward method, which is around handling a batch of data, chunking these to send over to your data parallel workers, because let's just say we're doing plain FSDP, and then you're going to collect the results with array.get. Okay, this said and done. If you look at how we could write down our training loop now, this is how like code might look like in a driver. This is a heavily like oversimplified view. But for example, what you could do is you could have your input batch of prompts that you could send to a similar inference actor group. And again, you would be slicing these and then sending them over to specific VLLM reactors and then collecting the results back into the driver. And then you would send this over to a different set of reactors in the environment actor group, which could be scheduled on a different set of nodes. And you'd collect observations and rewards back to your driver. And then finally, you might proceed and get your full trajectories, and you'll do something similar for components in your training. So you'd maybe have a critic actor group, and you'd perform a forward pass with the forward method that we described. And you can see how you're able to actually express complex data flow that I just talked about before with Ray. The single controller model, where the driver is orchestrating training at each stage, is also pretty intuitive to reason about, and you can iterate quickly with different ideas. It's also highly flexible. So the setup with like maybe FSDP actors that I showed there, you could actually swap that in with maybe say a deep speed or Megatron, while keeping your training code simple and also keeping your code focused around FSDP, just just managing around that rank and not worry about the higher level orchestration. You could also maybe change things around different backends, etc. Okay, so we've gone into details around training agents. I'll also talk very briefly around deploying agents with Ray. There's, again, a lot of complexity here. I won't go into too much depth because of time. But these are some user complaints that Ant Group had talked about in Ray Summit last year. And these are things around observability, around not having enough traffic control for heavy workloads, and also low GPU utilization. We can use RayServe, which is a library around online inference for a flexible, scalable, and efficient computation. It's Python native. You can mix business logic and machine learning and iterate quickly. And you get all the benefits of building on top of Ray with flexible scaling and resource allocation, etc. There's really two aspects as to how you could deploy agents with Ray. The first is around deploying the agent itself or deploying LLMs with the RayServe LLM API. What I've shown here is an example for actually serving DeepSeek R1. You get an OpenAI compatible API. You can let RayServe handle scaling and load balancing. You can scale to massive models, like I just said, DeepSeek R1. And you also get great observability with RayServe. The other aspect of deploying agents is deploying your tools itself, and you can also do that with RayServe. The example I've shown here is around deploying a remote MCP server and having RayServe handle scaling that for you. So again, the same aspects we talked about around auto scaling, load balancing, observability can again tie in here. And there's more details that I haven't got into, but you can read our official examples on this. But you can basically also have more complex composition of multiple tools, etc. And yeah, that's about it. We'd love to see more of you building and deploying agents with Ray, and it would be great for more of you to get involved in the Ray community. Thank you.
Thank you, Samant. Our next speaker is Daniel Han Chen, co-founder and CEO of Unsloth. He'll be speaking about training agents with reinforcement learning. Thank you.
Hello, everyone. Thanks for inviting me, and yeah, excited to be here. So today I'm going to talk about training intelligent AI agents with RL. My view is like RL is like the next, well, it is the next big thing for training any single agent that you like. So for people who don't know me, so I'm part of Unsloth. We help contribute a lot to the open source community. So last year we fixed like a gradient accumulation bug fix. We helped introduce something called async gradient, gradient offloaded gradient checkpointing. We also work with like multiple teams across the entire world, Hugging Face, the Gemma team from Google, the Llama team from Meta, Mistral. So essentially what we do is we fix bugs behind open source models. So like once you get like a model on your local device or like serve it in VLLM, we essentially fix the bugs but like behind the scenes. For example, we fix bugs in Gemma, Llama, Mistral, Phi, DeepSeek, many other models. And we have, I have a Twitter account if you want to follow that. I tweet about, the latest research and stuff like that. So definitely follow me on Twitter and stuff like that. And also, post about, possible model releases, for example, or, bugs in the models as well. Some other stuff that we do, like we fixed a few bugs in Phi 3 and 4 by Microsoft, multiple Llama 4 bug fixes. Now it's actually a very good model, so definitely try Llama 4 out. It's pretty good. You can run Llama 4 on your local device now, using Llama CPP, for example. We recently helped the Qwen 3 team on Qwen 3 Coda and other models. We do have a GitHub package as well, so we have like 40K styles in GitHub. We essentially make fine-tuning and RL much more efficient. And we have lots of free notebooks. Please use Google's free GPUs. They have a lot, so please utilize them. And we have 10 million monthly downloads on Hugging Face. So that's our GitHub package. Definitely check that out. And yes, again, please use the free GPUs. So today is about RL and stuff, and how is it related to agents. So in the old world, you will have like a final model. This is probably like a ChatGPT, a Claude, a Gemini. And so the goal is you start from a random initialization of weights, right? So like some random numbers, 1.4 trillion parameters, just random numbers. And the goal is to get to the green dot. And so imagine this is like some, 1.4 trillion parameter space, right? This is like 1D, but 2D. But the goal is imagine this is 1.4 trillion parameter space, and you're trying to move from the random initialization all the way to the green dot. And so the question is, how do you do this? And that is like just optimization, right? That's like gradient descent and stuff like that. We don't want to do that though, right? So essentially, we have found some tricks to make this faster. So the first step is pre-training, where essentially you can train to predict the next token. And so this is like maybe 13 trillion tokens, 30 trillion tokens, and you move from the black dot to the, the bluish dot, or whatever that color is. And that's called the pre-training step. And then we essentially then fine-tune the model with supervised fine-tuning or instruction fine-tuning to create ChatGPT or like a Claude or a Gemini. So the problem is if you just have a pre-trained model, it's kind of useless. It needs to follow instructions. And so that's the next step. This data is like, much less. It's not like 13 trillion tokens. It's much less. And then we do something called preference fine-tuning, or like DPO, RLHF, and stuff like that. This essentially aligns your model to respond, more favorably to like some requests. Like you don't want it to like randomly spill out some random instructions. And then finally, there's like this new paradigm called RLVR, where you want to do reinforcement learning with verifiable rewards, where you have like some tasks that you want to do, like good. You want to have the model solve math equations or like do coding. You want to like essentially make the model output this more correctly, and so you do this final step, and that's where you get the green dot. So that's the final model. There is a new paradigm recently where you want to skip actually from pre-training all the way to the green dot. So this is like you bypass the entire process. My view is probably not a good idea. You should probably still do the top parts and not bypass the process. The main reason is because this is actually quite inefficient. If you do want to do this, okay, fine. But my view is like you should do the top part still. Mainly for efficiency reasons. So like my view is like all of AI is all about efficiency. You could start from the black dot and go to the green dot directly, but you'll wait 1 million years. So like you have to like do these like special optimization tricks. So in terms of RL and agents, imagine that you're in this Pac-Man game, right? So this is how I like to explain it. You're essentially you're the yellow dot. You can move left, right, up, or down. So you have 4 actions, and that's the action space. You could eat a cookie, and if you do eat a cookie, you get a positive reward. But if you encounter one of your enemies, you'll get a negative reward. And so the goal of RL is to how do we maximize the best possible action and maximize reward, right? So how do we maximize the reward in this environment? And the difference is for ours, you actually don't know the best answer. For example, if you wanted to do normal fine-tuning or some normal supervised fine-tuning, you already know, oh, let's just avoid the enemies. But in RL, you actually don't even know that there are enemies. I mean, you don't even know that there are cookies. So the goal is you want to move in this environment automatically somehow and maximize the reward. A more concrete example is pretend I have a question. What is 2 plus 2? Okay, so the question is, what is 2 plus 2? You have a pre-trained model, and it will spit out, A, B, C, D, -10, infinity, I don't know, dog, cat, anything, right? So the correct answer is obviously 4, right? So the question is, how do you force the model to output the correct answer, 4? So my view is RL is kind of luck is all you need, patience, just wait. So essentially, the model will learn just by waiting. So you wait. It says A, it says B, it says -10, it says E, it says 3. Wait a second, 3 is closer, right, to the actual answer. You want 3, so you reward 3 a bit more than the rest, right? So for example, if you output a D or B or cat or dog, you'll give a very negative reward. But if you output some sort of number, you'll get some reward. And if you output a number that's very close to the answer, you'll get actually much higher reward. And so over time, you'll get -100, infinity, 10, and then suddenly you'll get 4, right? So maybe after 10 days, you'll finally get the answer 4. And then the goal of RL is, okay, I see this good answer, I want to maximize it. And so the algorithm kind of learns to maximize to get the correct answer. And so that's kind of my point is in R is kind of just patience and luck. So the goal is most likely large model labs, their view is okay, let's just wait for the model to learn. Maybe we can get to AGI. It's plausible, possibly. So the trick is your probability of the correct answer must be more than 0. If it's always 0, you're not going to go to AGI. But if it's a little bit, 0.00001, you might get to AGI. So I think that's their view. So in terms of algorithms, the most popular algorithm in the olden days was PPO. So PPO has 3 different models. There's a reward model, there's a value model, and then there's a generating policy and the reference policy. Well, technically 4, but I would just say 3. The trick is we have this new algorithm, GRPO, where we delete some models. This is all for efficiency reasons. Remember I said before, AI is all about efficiency. The whole goal is to reduce memory usage. So for example, we replace some parts with a ground truth reward function. You don't need a reward model anymore, it's gone. You can delete the value model, which estimates the average reward, gone. And this seems to work well due to DeepSeek R1 released this methodology. You don't just need to have a reward function. You can actually do many things in the blue box over here. You can do LLM as a judge. For example, you can actually call a language model to actually verify if the outputs are good or bad. You can do regular expression checking. You can do format checking. You can actually execute code on your device. Does this execute or not? And so these are the reward functions you can actually use in replacement of the blue box. I would say my view is large model labs, their view is can just use LLM as a judge. Just call the model to verify if the answer is good or bad, and just keep scaling this up to infinity. And maybe you can get AGI, maybe. But this is kind of the setup for modern RL systems. For GRPO specifically, the formula is a bit more complicated. I don't actually want to show the formula. I normally actually showcase this formula is a bit better. So the goal is you want to do the action that is much better than average. So you have to actually minus the average reward. You can't just optimize reward. You actually have to minus the base reward. So there is another thing called rollout or inference sampling. How does GRPO actually work? The trick is you want to utilize the LLM itself. Right? So for example, you ask the question, what is 2 plus 2? You ask the language model to generate 4 samples. Right? So it could be 0, 1, 2, or 4. So it generates those four things. Right? What we want to do is we want to reward the actual correct answer with 1, and the rest is 0. Right? So the other answers are bad, and 4 is the correct answer. And then we take this z-score, or we minus the mean divided by the standard deviation, and we use this as the actual reward. And why is it called group relative in GRPO? It's because you don't just do this once for one question. You do this more for many questions, right? So for example, what is 2 plus 2? You do 4 rollouts, right? You do what is 4 plus 4? You do 4. You know, create Python code, you do 4, right? So like you combine this all together in the RL system, and then that's why that's called group relative. And so there's actually many new research papers talking about like, you know, how to make GRPO better. You know, why is pre-training better than, you know, other things, like, you know, and why are the models easier to train over RL? There's many papers on this as well. Yeah, like a recent paper, Spurious Rewards. You know, highly recommend to read it. And you know, we do provide notebooks for you to like utilize RL and to make agents much more better. For example, like we show you how to like do formatting. We show you how to make reward functions. The most important factor for reward functions is please do more experimentation. And you know, there is a very common trend like, you know, don't just do RL first. You have to prime the model or do warm up with SFT. This allows your model to like learn the format first. So a big problem about RL is it just gets stuck in learning the format. So if you do, you know, RL warm up or SFT warm up, it will like skip that process. Yeah. Be careful with exact matches of regular expressions. One of the biggest problems I see with RL is when you do regular expressions, they don't work. So please manually verify if it's correct. Very common problem. And also, like, I think that's very, you know, I normally like to advocate is like distance scoring. Do not just score a reward as 0 or 1. Try to make a reward function as distance-based. For example, 2 plus 2 is 4. If it's 3, you don't just give it a score of 0. You should give it like a score of some score, right? So 3 is better than like minus 1,000. Yeah, and so we have lots of notebooks on our GitHub repo. Definitely check that out. Yes, lots of notebooks. Yes. And yeah, if you want to collaborate on anything, definitely reach out to me. And yes, I have stickers afterwards. So, you know, after the workshop and stuff, if you want to catch me up, yeah, I have stickers. Thanks a lot for inviting me.
Thank you, Daniel. And I would recommend everyone follow Daniel. I'm pretty much convinced he doesn't sleep. There's a lot of great tutorials online. And so our last speaker is Chitra Venkatash, product manager at Google, and we'll be speaking on A2A, the future of AI agent collaboration.
Hi, everyone. I'm Chitra Venkatesh, and I'm really excited to be talking here about agent-to-agent protocol and the future of agent collaboration. I'll be talking about 4 topics. The first, what's broken in today's agentic ecosystem, and what are the challenges and how we are addressing it through A2A protocol. Thirdly, I'll be talking about core features of the protocol. And lastly, I'll leave you all with some resources. So let's get started. What's broken with today's agentic systems? To talk about this, let me take a boilerplate example. An example of a trip planner. Typically, assume you have no agents right now. What would you do to plan your trip? You'll probably go to 3 or 4 websites or services, and maybe you use one for booking your flights, one for hotel reservations, one for your activities, and so forth. Now, imagine a world where each of these services come to you and they say that, hey, we have an AI agent that can offer these services. Wouldn't it be great if your flight agent could talk to your hotel agent and then say, hey, what's the check-in time? And based on that, I can reserve the flights. Unfortunately, as developers, we're not able to focus on this aspect of collaboration. Instead, we often find ourselves in cycles of these questions. Hey, which frameworks are these agents using? Where are they hosted? How do I discover these agents at the time of orchestration, and so forth? And if you're a provider, you're wondering, how do I make sure that people discover my agents, they know what my agent is capable of doing? If I have auth requirements, how do I make sure the other person knows about this, and so forth? This is exactly where agent-to-agent protocol comes into play. Without A2A, these agents are great, but great in isolation. They cannot work together. They cannot collaborate. With agent-to-agent protocol, we ensure interoperability and secure communication and collaboration between these agents. So let's talk a little bit more about the core features of the protocol. Firstly, agent-to-agent protocol is an open standard. It's designed to enable seamless communication and collaboration between agents, making sure that we have no more silos. And going back to our scenario of the trip planner, we're making sure that all those disparate agents are able to talk together and communicate. The key features here are secure collaboration, task and state management, negotiations, and discovery. Let's delve into each of these features a little deeper, and I'll be using the same reference again and again about the trip planner example. In terms of discovery, A2A agents explicitly list all their capabilities and skills using an agent card. Now, this agent card is a JSON file that's available at a well-known URL in the agent's domain. It's almost like a business card. It tells you what the agent is capable of. It can tell you whether the agent can stream, auth requirements, and so forth. So in the flight hotel example, let's say the flight example is looking for agents that can answer the question about check-in times. It's viewing agent cards of different agents, and it finds the hotel agent, and it sees that the hotel agent can probably complete that task for it. Next, once that discovery happens, the next point is negotiation. Agents are supposed to collaborate. They are not supposed to be wrapped as tools. It can be very limiting to agents. And this is where, again, agent-to-agent protocol comes into play. Agents can negotiate about output modality. Sometimes it could be other critical parameters that can greatly impact user experience. Going back to that flight and hotel example, the flight agent might say something like, hey, hotel agent, could you give me the check-in times in UTC? That's an example of negotiation. Once that negotiation and handoff happens, another issue we come across with is long-running operations. We often find ourselves trying to do long-running operations, and what we notice is you cannot always support these operations using synchronous communication. Agent-to-agent protocol has this concept of task objects. Every task object is associated with a task ID and a status. So every time, let's say, an operation or task gets created, you know what the status is, and then you can get notified because A2A also supports streaming with server-sent events. Going back to the example of the flight and the hotel agent may come back and say, hey, but I need to make a call to the hotel to find out the check-in times. This is going to take time, so I'm going to create a task with this ID and this status. Once I'm done, I'm going to send you a notification. This is again possible because we support streaming with SSE. Next, because all these agents are in different ecosystems, we really want to make sure the collaboration is secure. A2A supports secure collaboration because it uses HTTPS. Additionally, in the case of the flight and the hotel agent, we're making sure that the flight agent does not have access to the inner workings of the hotel agent, does not know anything about it, so we are maintaining that opacity. So summarizing the 4 key features: secure collaboration, task and state management, negotiation, and then discovery. Let's move to the resources section. So if you're interested to learn more about A2A protocol, you can find the documentation at a2a-protocol.org. The A2A project can be accessed at github.com/A2A project, and to install the Python SDK, just use pip install A2A SDK. If you're building using Google Cloud Platform, we provide an end-to-end toolkit for A2A agents on GCP. We offer native support for A2A in Agent Development Kit. ADK is another open source toolkit that can help you build agents. For deployment of options, we have several ways of deployment. If you're looking for a fully managed service, Agent Engine is the way forward. If you're looking for more flexibility, you can deploy A2A agents on Cloud Run and GKE. You can also bring your A2A agents to Agent Space. If you're looking for evaluation services, we support A2A agent evaluations on our Vertex AI evaluation service. You can also monetize your agents by publishing them on Agent Marketplace. We have seen immense response from the industry. We have loads of partners working, contributing. I just remembered from yesterday, there was a recent contribution from Twilio. They were looking to broadcast latency information. So let's say at the time of orchestration, they want to identify the right agent. They look for the latency of different agents and then choose the next right agent for that particular operation. So feel free to check that out. And I look forward to collaboration and contributions from all of you. Thank you so much for having me here, and go Bears on behalf of the A2A team. Thank you.
All right, thank you, Chitra, and thank you everyone for attending today. And I'd like to thank all of our speakers. I know it's particularly difficult to get your talks down to 10 minutes, but I really appreciate it, and thanks. And if you're interested in any of these open source projects, open standards projects, please get involved. Please engage with their communities. Thank you.